Oh my goodness, Crab Rave. Hello everybody, this is Husky Hacks back again for another walkthrough for the Huntress 2023 Capture the Flag challenge. We've got Crab Rave. This was one of the few hard challenges in this competition, and I even determined that this was so difficult that I gave everybody two options here. We've got Crab Rave easier and Crab Rave harder. So I initially developed this challenge as Crab Rave harder and then took a look at it and said that's actually too difficult for the challenge, so I'm going to make it a bit easier and give people the option. So for the purpose of this demonstration, I'm going to do two things here. I'm going to show Crab Rave easier, and I'm going to show the super mega unbelievably shortcut way to solve this, because the long way around, the scenic route to how to solve this one, is a lot of effort, and I will explain how you would approach it, but I'm not going to actually demonstrate it. I'm going to demonstrate the short way because I'm a busy guy. I got things to do. Okay, let's download it to our desktop and let's get working on this one. So right off the bat, I'll point out this thing is huge. If you took the easier route, this is a massive file, and you'll see why here in a moment. So just hang tight, grab a cup of coffee or something. I don't know. Okay, so that finished, so let's go ahead and unpack it. And we've got Crab Rave Easier. Let's bring this out to the desktop. Inside of Crab Rave Easier, we have two files. We've got one that is a hidden file. So if you see the little grayed out thing here, ntcheckosdll. ntcheckos.dll is a hidden file. And then this one, company financial report, safe no viruses.csv. So if we take a look at the properties of this file, it's obviously not a CSV. It's actually a link file. It's a shortcut file. And so the link file points to cmd.exe, and then we ping the local host a couple times, and then eventually we run DLL32 ntcheckos.dll and call to DLL main. Okay, so what is this doing? So this is kind of just like a little sneaky DLL execution payload. And so if you socially engineer somebody to click on this, they're not opening a CSV, they're actually calling run DLL32 to execute the DLL that's in this directory, which is ntcheckos.dll. And the comma there, and then the call to DLL main is the entry point for the DLL that they want to call. So this is just a little kind of like tradecrafty setup, but the real meat and potatoes of this challenge is ntcheckos.dll itself. So if we assume that all we're doing by double clicking on that is calling ntcheckos.dll and going to DLL main, well, let's go ahead and take a look at what that is. So like the immediate best approach here, I think, would be to open up Cutter or Ghidra or another disassembler decompiler, and let's go ahead and drop this thing into Cutter. And again, this is kind of a huge file. It's a DLL, but it is 12 megabytes, so it's actually pretty big. So let's go ahead and open up ntcheckos.dll. Remember, this is Crab Rave Easier, and so this is going to have a little bit more information available to work with. I'm going to load this in write mode, and you'll see why here in a moment. But let's go ahead and get the analysis rolling on ntcheckos.dll. All right, and after a little bit of waiting, there we go. We've got this open in Cutter. Okay, so what was Crab Rave all about? So from a high level, this DLL performs environment checks to make sure that the payload has landed on the correct target. So this is a super targeted, like APT or red team style environment keying payload. So it checks a couple of things on the host that it's detonated, and if those checks don't pass, the payload does not trigger. The checks have to pass in order for the payload to actually trigger. The payload itself is a create remote thread shellcode injection. In this case, it injects into notepad.exe and then pops a message box with the flag on it. But you can imagine that that shellcode is any other type of follow-on payload that you want, some kind of C2 agent or reverse shell, whatever, what have you. Okay, so how do you figure that out? So you've got to do a whole lot of reverse engineering to figure this out. So in Crab Rave Easier, debug symbols have been left in the payload. They've been left in the DLL. So when you go to things like the DLL main entry point, you can see the names of the functions that are called. Now, this is ntcheckos architecture is the exported function of this DLL. So it really exports two functions. DLL main is exported and ntcheckos architecture is exported. In turn, all that really happens is that DLL main calls ntcheckos architecture, but you could from run DLL32 call either of these. So both of these are known quantities, even in the harder version with the debug debug symbols stripped out, both of these are known quantities. But it's when you go into NT-check OS architecture that things start to get wild. If you're in the easier mode of this, debug symbols are still left in. But if you're if you're in the harder one, all of the symbols have been stripped out. And so you really have to dig deep for that one. And so if anybody actually approached the challenge that way and wants to do a write-up for it, please let me know. I'd love to read that. All right, so right off the bat, we've got some interesting stuff going on here, but we already know now that we're working in a Rust-compiled DLL. And so how do we know that? Well, one giveaway here is that we're working with something called litcrypt internal. And so this is a Rust crate. So let me actually go grab the docs, or really the source code for this. So litcrypt is a crate. So in Rust, packages are known as crates, and you install them, and they do different things. So they have nice, modular packaged functionality. So litcrypt is the literal encryption crate or package for Rust. So what this does is when you build your binary and you use litcrypt, you feed the binary an environment variable called the litcrypt encrypt key. You set a key in your environment variables on your development operating system, and that environment variable is passed in at compile time and is used to encrypt all of the string literals in your program. And so the string literals in your program are only ever decrypted when they're used in memory at runtime, and then they're immediately re-encrypted. So this is like a super sneaky way to be hiding strings inside of your program. But this is a dead giveaway that we've got the litcrypt internal crate calling the decrypt bytes function. And so the output from each of these times that litcrypt internal is called is going to be an encrypted string literal that's passed around the program. So what ends up happening here, I think a little bit further down here, is that we are performing two different checks in this environment, right? So when this payload is triggered on a Windows operating system, it runs two checks. It calls the whoami platform username function. So whoami, again, is another crate in Rust. And it calls the platform hostname function. So it's calling the username and the hostname. It casts those into lowercase, and then it checks those against these two litcrypt encrypted string values. So from a high level, we're doing two environment checks immediately. We're checking the username and the hostname. Both of those have to match in order for this payload to trigger. If those both match, just scroll down through all this insanity here. If both of those match, so we call to the, pattern is contained, so it's checking if the string is contained in the value that it found. So all of those checks are rolled up into a Rust enum, and the enum is checked for a Boolean true or false. So did this enum pass? Did all of the environment checks pass? And then it drops into this code block right here, which is the key to this. Now remember, again, I want to stress, Rave Easier had all of the debug symbols left in, so you can see Rave litcrypt internal decrypt some bytes, and then you can see Rave inject flag. So you could pretty quickly identify where the flag was being injected. In Rave Harder, that was not the case. You had to go do this all manually, essentially, and figure that out. But eventually, we drop into this code block here. If the environment checks passed, we inject the flag. We actually end up decrypting another string here, which is the string of the process name to inject into. In this case, it was notepad.exe. And then we call inject flag. So the super quick, shortcut, easy way to solve this challenge was the following. All right, so in NT-check OS architecture, we will go down in the graph view until we find the block where the injection takes place. And so let's see, we've got the whoami and the hostname calls there. We keep going down here. We've got the two lowercase, and we've got, here is the execution of the actual flag injection. So we do a little bit of setup for this. We call litcrypt internal decrypt the bytes. That's the process name. That's notepad.exe. And then we pass that into the inject flag routine. So what we can do is in the disassembly, we can take note of the block of code where this happens, right? So let's go over to the disassembly, and this is our memory offset location of the flag injection, right? Now, I want to harken back to like what we did for rock, paper, psychic and just binary patching in general. There's no reason why we can't just patch the bytes of this binary to jump straight to, basically short circuit the binary and jump straight to the point where the flag injection takes place. And so if you and it takes a lot of like work to get to that point. But if you find out that the environment keys are checking the username and the host name, and then you find out that there's a code path where the injection actually takes place, it doesn't matter what the flow is to get there. You can short circuit the binary to go straight there. And you could do that by editing the instruction here. And instead of this JE, so we're starting right at the beginning of NT-check OS architecture, we can just do a jump right to the location of that injection where it takes place. So if we save, and then we can actually reopen this, which might take a second. So let's just let the save go through, and then we'll try to reopen this, and we'll look at the graph view again and see the difference. So I'll save. All right, and we're back in. Let's go back into NT-check OS architecture. And when we go to the graph view here, look at this. We've got from calling NT-check OS architecture, which again, remember, is called from DLL main. We do the setup. We set up our stack frames. We call 2 instances of decrypt to get 2 of the environment keys. But then look at this. We jump right to, without any kind of conditional check, without going to any side of the code path, we jump immediately to decrypt the name of the process where we want to inject and then inject the flag. So we have bypassed, by patching this, we have bypassed those environment checks, and we go right to the inject the flag routine. And we can prove that by doing the following. Let's go to the desktop, and let's do run dll32.exe. We're going to call ntcheckos.dll with a comma, and then dll main. Problem starting ntcheckos. This is being used by a different process. Okay, we just have to close that in Cutter then. That's okay. And let's run it one more time. And over on my other screen here, Notepad just popped up, and then we count 3, 2, 1. And then I think right behind it, we should have gotten the flag. Yep. So that popped up on my other screen, but that's the flag injection of the message box for the flag right there. Now, another gotcha here is that if you got to the point in your isolated lab environment where it performed the flag injection, the flag was stored in a GitHub gist file under my GitHub account, so you needed to have access to GitHub, in other words, internet access, to actually grab the flag. So that was like one potential hurdle there. If you got to the point where you could coerce the flag to inject, it would attempt to inject the bytes by grabbing them from that GitHub gist file and then decoding the base 64 and then AES decrypting the shellcode and then injecting into notepad.exe. So that was Crab Rave. I expect tables to be flipped over that one. That was not easy, but I hope you had fun with that. And I hope you learned something as well. And one last thing before we wrap up here. If you're interested in learning how to write malware that does that kind of environment checking stuff, I run a course over on the Taggart Institute called Responsible Red Teaming that goes over that TTP and a whole bunch of other things that have to do with red teaming in a responsible, ethical fashion. This course is pay what you wish, including $0. It can be free if you decide, but if you want to throw me a few bucks for it, hey, I really appreciate it. But that's over at the Taggart Institute, so that's taggartinstitute.org, and I will link that in the video description below. So go there if you're interested in learning how to write malware in Rust that performs those environment checks. And that's it for Crab Rave. I hope you enjoyed it.